My name is David Gillespie, and I am doing a presentation on low thrust trajectory optimization in LEO for Aero 557 at Cal Poly San Luis Obispo. Low thrust trajectories are where very small constant thrusts are introduced into orbits. Methods of propagation such as Cowell's method and Inca's method that are traditionally used in other orbital propagations do not work with low thrust trajectories because these small thrusts are eaten up in the errors in the propagation functions. So variation of parameters is used instead because it captures these small thrusts very well. It propagates the classical orbital elements of the orbit instead of the position and velocity. The equinoctial element set is a variation of the variation of parameters that uses different elements that are propagated in order to get around the values in the denominators that cause variation parameters to break down with low inclination and low eccentricity orbits. So applications for low thrust systems in geosatellites, there is station keeping that's performed, and that could theoretically be performed in LEO satellites with low thrust systems. Low thrust systems could also be used to perform large plane changes in LEO, where using a high thrust system would cost significantly more mass. A system like this could theoretically be used to capture orbital debris transferring into multiple LEO orbits before finally deorbiting all of the material plus the system. And also small sats can use low thrust systems to maneuver into specific orbits. Variation of parameters, Gaussian and equinoctial, just a summary of the equations that are propagated. The Gaussian form of the variation parameters has the classical orbital elements with either the angular momentum or the semi-major axis being propagated for the first term, and the next 5 terms are always the same. Equinoctial elements are a modification of the Gaussian elements, where the first term is based off of the semi-major axis and the eccentricity of the orbit, and the rest of the parameters are largely based off of the true anomaly, the right ascension of ascending node, the inclination, and the argument of perigee. Propagation of orbits in VOP is costly in terms of calculation time because there are 6 elements or more being propagated at the same time. So methods of averaging are sometimes used to reduce the time needed for calculations. Relatively, orbits aren't altered quickly by perturbations, so the averaging holds for the usual perturbations in low thrust systems. To further reduce calculations for coplanar transfers, sometimes only the semi-major axis, eccentricity, and inclination are used, and then if a specific element is known to be changing, that element is also used. So from the lecture, propagation method that we use is orbit averaging, where the orbit's propagated by a low order solver to get the average value over a specific amount of time, and then we can also throw in J2 perturbations, and that is actually just thrown in over an average amount of time because we have the J2 perturbations, the rate for the change in right ascension and argument of perigee. And there are large sine and cosine functions for the optimal control laws for this propagation method. In the Varga and Perez paper cited in this presentation, the optimization method they use has a modified Lyapunov feedback control method with equinoctial elements called the Q law, and they use this to determine optimal thrust angles and coast bases for a transfer orbit. The Q law function is shown at the bottom of this slide with W as a weighting factor and S as a scaling factor. Variation in the weights causes different types of optimizations due to the different elements in the equinoctial set that it is varying. So the set of equinoctial elements that they use is shown here. The full equations are not shown because they are long and very complicated, but they are referenced in a previous article written by the authors, and the F values at the bottom right are substituted in to get a maximum rate of change of the equinoctial elements. When optimizing, the algorithm optimizes the thrust angles such that the derivative for Q is always negative, and therefore Q, the whole function, always decreases and is minimized. The derivative for Q is shown below, and the partial derivative with respect to each control angle is also shown below. So for the Begg article, they look for an optimization method that is fast, accurate, and robust for LEO orbits. The orbits are optimized using a minimum principle, which gives necessary conditions for the command law to be locally optimized. The orbits are then optimized based off of minimizing time, which is which is used via the MIP ELEC code, and then the orbits are optimized a second time based off of that minimized time, but now for minimizing mass, and a T3D code is used for this. Preliminary filtering of the results is done to throw out infeasible orbit transfers, since it is a low thrust system. Equation to the right shows the raw estimate for the necessary delta V for a transfer between two circular orbits without J2 perturbations. The basic check is if the delta V needed for any of the optimized orbit transfers is greater than 10% of this value, it's not a low thrust transfer. The orbits with J2 effects in them have several different methods to calculate the delta V. So once feasible orbits have been found, different algorithms are used for the J2 perturbed and the unperturbed orbits. For the unperturbed, the MIP ELEC code is used to get a first time minimized solution with a high thrust, and that just gets a very quick and dirty answer. The T3D is then run with a lower thrust and a longer time, and iterated down to the thrust target value, with a final minimum transfer time being the output of this process. And then the same process is then applied to the fuel minimized case, with the transfer time starting as the minimum transfer time from the last step. And then an increased transfer time with each iteration for this step decreases the delta V, resulting in a fuel minimization. And then for perturbed case, the same basic thing happens, except there is a branch for cases that do not close, which is resolution by fragments, and it is similar to the burn coast burn trajectory solutions that we have learned in class. And the orbit is essentially broken up into the initial burn, a coast, and final burn, and that helps with convergence issues in the algorithms and the codes used. And the algorithms for this method require good initial conditions for the orbits in order to close quickly, because some orbits may not be feasible to transfer in between, and then also some of the results may be very unique, and so they need to be filtered carefully so that unique orbit transfer solutions aren't missed. Thank you, and here are the references.